Let's start by looking at software transactional memory, or STM. This is a way to manage multiple pieces of shared memory so that they can be updated together in a safe and consistent way. The key point is that these updates happen atomically, meaning all at once or not at all, which helps avoid errors that can occur when multiple processes try to change data at the same time. STM does this without using traditional locks, making the process simpler and often more efficient. The visual here highlights the concept by showing a large circle representing software transactional memory, emphasizing its role in controlling concurrency. The key idea behind software transactional memory is that a group of memory operations either all succeed together or none of them take effect. This means that if any part of the operation fails, all changes are rolled back, keeping the system consistent. STM provides transactional semantics, which work much like database transactions, but apply to in-memory data structures. This ensures that complex updates happen atomically, which makes concurrency easier to manage and reduces errors caused by multiple threads accessing shared data at the same time. Traditional lock-based concurrency control often runs into problems like deadlocks, where processes get stuck waiting on each other indefinitely, and priority inversion, where higher priority tasks are delayed by lower priority ones. It also involves complex lock ordering, which can be hard to manage correctly, and poor composability, meaning it's difficult to combine smaller concurrent operations into bigger ones safely. STM tackles these challenges by removing the need for explicit locks, which reduces complexity and the chance of errors. It automatically retries operations that conflict, ensuring that changes only go through when it's safe to do so. Finally, STM keeps multiple shared states consistent all at once, giving you a simpler, more reliable way to handle concurrency. In closure, software transactional memory is built around two key parts, refs and transactions. Refs are the shared, mutable references that hold the state you want to manage concurrently. Transactions are blocks of code that safely update these refs, ensuring all changes happen atomically and consistently. When you run code inside a transaction, closure guarantees that either all the updates to refs succeed together, or none of them take effect if a conflict happens. This approach helps avoid common concurrency problems like deadlocks and keeps your state consistent without needing explicit locks. Refs in closure are mutable references that always point to immutable data, which means the data itself doesn't change directly, but the reference can be updated to point to new data. These refs allow multiple coordinated updates through transactions, ensuring that all the related changes happen together atomically. Importantly, any changes made within a transaction are not visible to other parts of the program until the transaction commits successfully, which helps maintain consistency and avoid partial updates being seen. This approach aligns well with STM's goal of safe and predictable concurrency by coordinating state changes cleanly and reliably. Here are two references in closure representing account balances. The first one, balance A, starts with a value of 1000, and the second, balance B, starts with 500. These references are special mutable containers that hold immutable data, and they are used within transactions to ensure that any updates happen in a consistent way. Changes to these refs won't be visible until the transaction they're part of successfully commits, which helps manage concurrency without locks. This foundation lets us safely update shared state while avoiding common pitfalls like deadlocks or race conditions. When working with refs in closure, all changes must happen inside a special block called dosync. This block defines a transaction, which makes sure the updates are coordinated and either fully succeed or don't happen at all. For example, if you want to transfer 100 units from one balance to another, you use dosync to alter both balances together. If any conflict happens during this process, like another transaction changing the same refs at the same time, the whole transaction is automatically retried until it can complete without issues. This approach ensures consistency without the complexity of manual locking. When we talk about consistency guarantees in STM, there are four main properties to understand. Atomicity means that all changes to refs within a transaction either happen completely or not at all, so partial updates don't occur. Consistency refers to preserving any conditions or rules you define on your data, ensuring the system remains in a valid state after each transaction. Isolation means transactions appear to run one after the other, even if they run concurrently, so the effects are serializable without interference. Lastly, durability isn't provided here since this STM operates purely in memory, so changes are lost if the system stops or crashes. This setup balances strong correctness guarantees with the flexibility of in-memory operations. The optimistic concurrency model used in STM works on the assumption that conflicts between transactions are uncommon. Each transaction runs speculatively, meaning it proceeds without locking resources beforehand. During execution, all reads and writes are carefully tracked. When a transaction tries to commit, the system checks for any conflicts with other concurrent transactions. If a conflict is detected, the transaction doesn't fail outright. Instead, it automatically retries until it succeeds without conflicts. This approach avoids the need for blocking locks, which can cause delays or deadlocks, and it also enhances composability, allowing multiple operations to be combined more smoothly within transactions. When working with software transactional memory, it's important not to include side effects inside the dosync block. This is because transactions can be retried if conflicts occur, and any side effects inside the transaction might run multiple times unintentionally. For example, if you're modifying state and also triggering something like logging, sending a network request, or updating an external system inside dosync, these actions could repeat with each retry, leading to inconsistent or unwanted behavior. Keeping side effects outside ensures they happen only once and don't interfere with the transactional consistency or retry mechanisms. Here, we see how to properly combine software transactional memory with agents to handle side effects safely. We define an agent called logger to manage logging actions and a ref called balance to hold the account balance. Inside the dosync transaction, we update the balance by decreasing it by 100 using alter, and then send a message to the logger agent to print balance updated. The key point is that the agent's action runs only after the transaction commits successfully, ensuring that side effects like logging do not happen inside the transaction itself. This avoids the problem of side effects being executed multiple times if a transaction retries, keeping our state updates consistent and our side effects well managed. STM is best used when you need to update multiple shared states at the same time, especially if you have invariants that must always be preserved to maintain correctness. It's also the right choice when consistency is more important than minimizing latency, as STM ensures all changes commit together atomically. On the other hand, you should avoid STM if the state updates are independent and don't need to be coordinated. It's also not a good fit for long-running operations because transactions retry on conflicts, which can cause delays. Additionally, STM struggles with hotspots where many transactions try to update the same data simultaneously, leading to high contention and reduced performance. Understanding when to apply STM helps balance the trade-offs between consistency, latency, and concurrency in your system. STM provides a way to coordinate shared state updates by treating them as all-or-nothing transactions, ensuring that either everything changes together or nothing does. This means that the shared state, managed through refs, remains consistent and transactional, preserving user-defined invariants. The dosync block is where these transactions occur, running speculatively and automatically retrying if conflicts are detected, so the system handles concurrency optimistically. This approach helps manage complex state changes safely, as we discussed with atomicity, consistency, and isolation earlier, making STM a powerful tool when multiple related updates need to happen together without stepping on each other.